Hello, I'm Professor von Schmohawk, and welcome to YU. In the last several lectures, we introduced several forms of linear equations whose graphs are lines in the xy plane. In this chapter, we will use linear equations to solve some real-world problems.
Why, hello, Hulk! I'm so happy to see that you are gainfully employed this summer. I was looking for someone to drain my pool tomorrow.
Sure, Professor Atheline, but I'm supposed to clean Mr. Squeegiopolis' pool tomorrow.
Well, I'm sorry, Hulk, but I need it drained by 8 p.m. tomorrow. I'm having some very important guests over, and the pool must be completely empty by the time they arrive.
Okay, Professor, I'll figure something out.
Oh, Hulk, you're such a resourceful young man. I knew I could count on you.
What's the matter, Hulk? Have you perhaps encountered a small resource scheduling problem?
Okay, Geekman, how much is this gonna cost me?
Well, my normal short notice subcontracting fee is $50 an hour, but I'm running a special today. Only 49 buckaroonies an hour.
Yeah, well, I'm running a special today on knuckle sandwiches.
Perhaps I didn't mention that you're eligible for the double extra special very best buddy rate of $3 an hour?
Well, just make sure you have that pool empty by 8 p.m. tomorrow.
Yes, sir, Mr. Bushmasher. Rats, it's almost noon. I'd better get cracking. Start pool draining at 12 noon. It's 1:30 and the water level is 10 feet. Hmm, 3 o'clock and the water level is 8 feet. Yikes, this pool better be empty by 8 p.m.
Well, it looks like ace algebra student A.V. Geekman may be in hot water. Will the pool be empty by 8 p.m.? If we graph the water depth versus time, we might be able to figure out how long it will take for the pool to completely drain. We will plot the amount of time since the drain was first opened at noon on the horizontal axis and water depth on the vertical axis. We know that at 1:30, 1.5 hours after the drain was opened, the water level was 10 feet. And at 3 o'clock, after 3 hours of draining, the water level was 8 feet. However, there is one problem. With only 2 data points, it is impossible to determine whether the water level is dropping by the same amount every hour, or if the water level drops more quickly as time goes on, or perhaps if the water level drops more slowly with increasing time. Taking one additional measurement a third time would allow us to determine which scenario more accurately represents the water level as a function of time.
Dang, it's 6 o'clock already. And we still have 4 feet to go.
We can now add a third data point to our graph of water depth versus elapsed time, since AV has determined that after 6 hours, the water depth is 4 feet. It looks like these 3 points all fall on a line, so maybe the function we are graphing is linear. We can verify this mathematically by calculating the slopes of the line segments connecting the first and second points, and the second and third points. If the slopes of both segments are the same, then all 3 points must lie on the same line. As we saw in the chapter on slope, we can calculate the slope of a line which passes through 2 points as the difference in the point's y-coordinates, delta y, divided by the difference in their x-coordinates, delta x. Dividing delta y by delta x, we get -4 over 3, or a slope of -4/3. Now let's calculate the slope of the other line segment. Once again, we take the difference in the y-coordinates, delta y, and the difference in the x-coordinates, delta x. Dividing delta y by delta x, we get -2 over 3/2. We can simplify this complex fraction by dividing -2 by 3/2. This is the same as multiplying -2 times the reciprocal of 3/2, or 2/3. -2 times 2/3 is -4/3. So the slope of this line segment is also -4/3. Since the slopes of these two connected line segments are the same, all 3 points must lie on the same line. We can therefore assume that the water in the pool is draining at a constant rate and that the water depth as a function of time is linear. Since we know this line's slope and at least one point which falls on the line, we can write the equation for this line using the point-slope form. If we choose the bottom point, which has coordinates 6, 4, to use as the known point in the point-slope formula, then x1 is 6, y1 is 4, and the slope m is -4/3. Now that we have an equation which represents water level y as a function of elapsed time x, we can plug in different values for x to see what the water level will be at those points in time. For example, an elapsed time x of 0 corresponds to the time when the drain was first opened. If we set x to 0, then the resulting value of y will tell us the initial depth of the pool. Completing the arithmetic, 0 minus 6 is -6, and -4/3 times -6 is +24/3, or 8. Adding 4 to both sides of the equation allows us to cancel -4 on the left, leaving us with y equals 8 plus 4, or 12. So the initial depth of the pool when the elapsed time x was 0 was 12 feet. If we would like to find out how long it will take for the pool to be empty, we can set the water level y to 0 and solve the equation for x to see what the elapsed time is at that point. We start by setting the value of y to 0, and we can then write 0 minus 4 as -4. Since we are trying to find the value of x, we want to rearrange the equation so that x is alone on one side. To do this, we must first eliminate the -4/3 by multiplying both sides of the equation by the reciprocal of -4/3, which is -3/4. Since anything multiplied by its reciprocal is 1, we can replace -3/4 times -4/3 with 1. Now, since everything in the parentheses is multiplied by 1, we can eliminate the 1 and the parentheses. Completing the arithmetic on the left side, -3/4 times -4 is 12/4, or 3, and adding 6 to both sides allows us to cancel the -6 on the right, leaving us with the equation 3 plus 6 equals x. Adding 3 and 6, we have 9 equals x, or equivalently, x equals 9. So when y is 0, x is 9. Since x is the elapsed time, and y is the water level, This result tells us that when the water level y is 0, the elapsed time x will be 9 hours. Since the drain was opened at noon, the pool will not be empty until 9 o'clock.
Excuse me, Professor von Schmohawk. Did I just hear you say that my pool will not be empty until 9 o'clock?
Yes, Professor Etheline. According to all calculations, that is correct.
But I distinctly remember telling Mr. Moose Masher that my pool must absolutely be empty by the time my guests arrive at 8.
Excuse me, if I may interject here for a moment. I believe that it is possible to calculate the exact depth of water in your pool at the time your guests will arrive. If we start with the equation for water depth versus elapsed time, and set the elapsed time x to 8 hours, we can then solve this equation for y, which represents the water depth, and thereby determine the depth at exactly 8 o'clock post-meridian. As we all know, 8 minus 6 is 2, and negative 4/3 times 2 is negative 8/3. Then, adding 4 to both sides, the 4's on the left side cancel. We can then write 4 as 12/3, and negative 8/3 plus 12/3 is 4/3. So, according to my calculations, the water depth at 8 o'clock p.m. will be exactly 4/3 feet. In other words, 1 1/3 feet. Now, since there are 12 inches in a foot, 1/3 of a foot is 12 inches divided by 3, or 4 inches. So, 1 1/3 feet is 1 foot 4 inches. We can therefore deduce that when your guests arrive, your pool will contain exactly 1 foot 4 inches of water. Nope. Professor Etheline, how much longer do I have to entertain your guests?
Why, you're doing a splendid job, AV. I'll let you know when it's 9 o'clock.
Yeesh.
Clock, and just as calculated, the pool is empty. Oh, my!
Hello! I'm Professor von Schmohawk. How linear equations can be applied to real-world applications. These equations express mathematical relationships between numeric quantities. For example, the relationship between the level of water in a pool and time. Many real-world quantities can be calculated using formulas which relate two or more quantities. For example, we can calculate the perimeter of a rectangle by adding twice its length to twice its width. This formula relates three quantities: perimeter, length, and width. Instead of using words to represent these quantities, we can write this more compactly using letters like P, L, and W. Formulas for calculating the value of one unknown quantity from one or more other quantities whose values are known are sometimes called literal equations. The word literal refers to the fact that when calculating the unknown quantity, variables in the formula are replaced by the actual or literal values corresponding to a specific case of the relationship. Literal equations can involve more than three variables. For example, the formula for calculating the volume of a rectangular box, otherwise known as a rectangular prism, is V equals L times W times h. In this equation, there are four, which are V, which represents the volume of the box, and L, W, and H, which represent its length, width, and height. Likewise, literal equations may involve only two variables, as in the formula to convert temperature in degrees Celsius to Fahrenheit. In this formula, the variables are C, which represents the temperature in degrees Celsius, and F, whose value is the temperature in degrees Fahrenheit. The value of any variable in a formula can be calculated given known values for the other variables. Therefore, it is often desirable to rearrange the formula so that the variable whose value we wish to calculate is alone on the left side of the equation. For example, we could rewrite this formula to calculate degrees Celsius given a known temperature in Fahrenheit. To calculate degrees Celsius, it is desirable to rearrange the formula so that C is alone on the left side. The first step is to isolate the term containing C on one side of the equation by moving all the terms which do not contain C to the other side. Subtracting 32 from both sides of the equation allows us to eliminate the 32 on the right side. We say that the terms 32 and negative 32 cancel, since together they equal 0. Eliminating these terms on the right accomplishes our goal of isolating the term containing C. Since we want to end up with the variable C alone on one side, we must also eliminate the 9/5 multiplier. We can do this by multiplying both sides of the equation by the reciprocal of 9/5, which is 5/9. Since anything times its reciprocal is 1, 5/9 times 9/5 can be replaced by 1, and 1 times C is just C. Swapping the two sides of the equation, we now have a formula which calculates the value in degrees Celsius for a temperature given in degrees Fahrenheit. Another example is to rearrange the formula for calculating the perimeter P of a rectangle given its length and width to create a formula for calculating the length L given the perimeter and width. Just as before, we want to rearrange the formula so that the variable whose value we are calculating is alone on the left side. We start by subtracting the term 2W from both sides of the equation. This allows us to cancel the 2W term on the right, leaving only the term 2L. Since we want L alone on one side, we must eliminate the multiplier 2. This can be accomplished by dividing both sides of the equation by 2. Since identical factors in the numerator and denominator of a fraction can be cancelled, we can cancel the 2's in the top and bottom of the fraction on the right, leaving only L. Swapping the two sides of the equation, we have a formula which calculates the rectangle's length L, given known values for its perimeter and width. Let's say that we are given a formula A equals B over 2C and are asked to solve this equation for C, given known values for A and B. To solve for C, we want to rearrange the equation with C alone on the left side. To rearrange the equation so that C is alone on the left, we must first move C out from the denominator of the fraction. We can do this by multiplying both sides of the equation by C. Multiplying the fraction on the right by C is the same as multiplying the fraction's numerator by C. We can then cancel the C's in the numerator and denominator. We must now eliminate the variable A on the left so that we end up with C alone on the left side. To do this, we divide both sides of the equation by A. The A's in the numerator and denominator on the left then cancel, leaving C alone on the left. We can simplify the complex fraction on the right, since dividing the fraction b over 2 in the numerator by a is the same as multiplying b over 2 by the reciprocal of a, which is 1 over a. Multiplying the numerators and denominators of the two fractions gives us b over 2a. Since this equation now contains the variable c alone on the left side, we have solved the equation for c. As another example, let's start with a similar equation, except with an additional term on the right side, and solve for the variable a. To rearrange the equation so that a is alone on the left side, we start by subtracting the term 5d from both sides of the equation. Since we want the variable of the fraction on the right, now eliminate the terms in parentheses so that the and cancel those terms in the numerator and denominator of the fraction 2 by the multi. Sometimes we may wish to solve the left side. We'll start equation. Allowing terms containing n are now collected on the left. All the terms containing n are now collected on the right. Now all the terms without n are on the right. N alone on the. This can be accomplished by placing the two terms in parentheses and then using the distributive property to bring the common factor n outside the parentheses. The variable n is a parentheses, and if we like, we can change the sign of the numerator and the fraction on the right to 1. This flips the sign of the numerator and the signs of both terms in the denominator. The positions of the two terms in the denominator can then be swapped. Since the variable n is alone on the left side, we have solved this equation for n. In the last several lectures, we have studied linear equations and shown how they can be applied to some real-world applications. In the next lecture, we will show how to create linear equations which can solve various types of real-world problems. In the last several lectures, we studied linear equations and saw several examples where they were applied to real-world applications. In the next few lectures, we will show how to create our own linear equations for solving various types of real-world problems. For example, every New Year, Adrian Scienstein's wealthy uncle Monopolis gives Adrian, her big brother, and her little sister each a cash gift of $10 for each year of their age. Adrian's big brother is 3 years older than Adrian, and her little sister is 7 years younger. This year, the gifts we start by so how old? This year, the gifts total $500. So how old is Adrian? Find Adrian's age. Is Adrian's age Since their uncle is giving them a total of 5 ages, we can now solve this linear equation like 3 plus 3 as negative 4. Change the equation so that x is alone on the left side. 4 to both and positive 4 is 4's. X equals 54. by dividing in the numerator until x equals 54 over 3. Stage x is 8. Expression is 21. We can check to see if Uncle gave them 10 would have indeed totaled $500. Our approach to solving this problem is a good example of typical steps used when solving real-world problems with algebra. We start by assigning a variable to the quantity we want to find, and then try and write other quantities in terms of that variable. We then create an equation which relates the quantities, simplify the equation, and solve for the unknown variable. Once the value of the variable is known, we can then calculate other quantities which may be of interest. Finally, we check the answer by recreating the equation using the quantities we have calculated and making sure that everything seems reasonable. Now let's try an example involving the perimeter of a rectangular room. We are told that the length of a rectangular room is 5 feet longer than its width. If we know that the perimeter of the room is 90 feet, then what are its length and width? Since we want to find the room's length and width, we can assign the unknown variable to either of these quantities and then write the other quantity in terms of that variable. Let's let the variable w represent the width of the room. Since the length of the room is 5 feet longer than its width, we can write the value of the length as w plus 5. Adding the lengths of the four sides of the rectangle, we get the total length of the perimeter, w plus 5 plus w plus w plus 5 plus w, which must be equal to the perimeter, 90 feet. Collecting like terms, we group all the w's together on the left. We then simplify the equation by writing w plus w plus w plus w as 4w and 5 plus 5 by subtracting 10 from 10 and putting the arithmetic, writing both numerator, leaving u equal. We see that the width of the room is 20 feet and the length is 25 feet. This solution is reasonable, since we are told that the length of the room is 5 feet longer than its width, and the sum of the lengths of all four sides, 25 plus 20 plus 25 plus 20, is equal to the perimeter, which is 90 feet. For our next example, let's try a slightly more complex geometrical problem. We are asked to build 3 identical dog pens where each pen's length is twice its width plus 3 feet. We are told that the pens are to be built side by side so that each pen shares a fence with the adjacent pen. We are also told that we have exactly 180 feet of fence, all of which must be used to enclose and separate the pens. However, we are not told the dimensions of the pens. Fortunately, using algebra, the length and width of the pens can be calculated. To find the length and width, we assign the unknown variable to either quantity and write the other quantity in terms of that variable. Let's let the variable w represent the width of a pen. Since the length of a pen is twice its width plus 3 feet, we can write the length as 2w plus 3. Adding the lengths of each fence segment, the total length of the fence is 2w plus 3 plus w plus w plus 2w plus 3 plus w plus w plus 2w plus 3 plus w plus w plus 2w plus 3, which is equal to 180 feet.